Hello, welcome back. In this lecture, we are going to discuss the data representation, because in the first two lectures, we have introduced the structure of the computer and the hardware of the computer. Modern computers are multimedia computers. Means that the computers can handle different type of media data, like numbers, text, audio, video, images. So in order to process this different type of data, you have to represent the data and to store the data in the computer. So in this lecture, we are going to study how to represent numbers first. You will be able to know the different type of number systems and how to represent different number systems in binary. You're also going to know how to convert from one number system to another number system. We're also going to study the logical number and how to represent logical numbers. Let's look at the number system first. If I give you this number, you probably think, okay, this number is 642 because we have a 6 here, and this is supposed to mean 600, and this 4 here means 40, this 2 means 2. But why this 6 not means 60 or 6, but it means 600 because of its position? So the value of the number is not decided by the number itself, but also decided by the position. So we can get the value of this number by this formula. So we use 6 times the position value, which is 100 for this one. We got 600. And then we plus 4 times the position value, which is 10. We got 40. And then we get 2. So if we add them together, we got 642. So this is the value of this number. Because this number is a decimal number, so the value of this number is the same as the number. We call this positional notation, meaning that the value of the number is not only decided by the number, but also decided by the value of the position. Because the number is decimal, so the base is 10. So we call this base 10. And we call this the power. So the power indicates the position of the number. As you can see from this example, so the power for this 6 is actually to the second power of 10. And the power for this number is actually 10. And the power for this number is 1. So the power and base is the important concept for the positional notation. So if we know the base and power, we should be able to know the real value of a number. Even though the base of the number maybe not 10, let's say 11 or 12, we can still get the real value of the number. So the number systems has a base. For example, there are 12 months in 1 year. So in this number system, the base is 12. There are 7 days in 1 week. So in this number system, the base is 7. There are 60 minutes in 1 hour. So the base for this number system is 60. So the base of a number system determines the numbers of digits in the number system and the value of digits position. A carry means a carry will be performed when the sum of two numbers is greater than the largest digit in the number system being used. For example, we have 7 plus 9. It actually equals to 12, right? But because this is in decimal, so the largest number is actually 9. So if we use like 3 plus 9, and we got 12 here, but we need to have a carry. So this is called the carry. So the carry is 1. So we get 12. And we have a small video here to introduce the brief history of number systems. And you can check out this video. The numbers we used in the computer system are not decimals. We used binary to represent the numbers. And binary is a special number system. It only has 2 digits, 0 and 1. We use a unit called bit to measure the numbers of the digits. So therefore, 1 bit can represent only 2 things, 1 or 0. To represent more than 2 things, you need multiple bits. For example, 2 bits can represent 4 different things, 0, 0, 0, 1, 1, 0, and 1, 1. So if you want to represent more than 4 things, you need more bits. Like 3 bits can represent 8 different things. So in this slide, we showed you how to represent more different things using binary. So 3 bits can represent 8 different things, and 4 bits can represent 16 different things, and 5 bits can represent 32 different things. So this is the binary. As you can see, all these numbers only include 1 or 0. There's no other digits. In general, n bits can represent 2 to the nth power of different things, because there are this number of combinations of 0 and 1s that you can be made from n bits. Note that every time we increase the number of bits by 1, we double the number of things we can represent. You may think binary is not as powerful as decimal, because decimal have 10 different digits. Why don't we just use decimal to represent the data in the computer? It's because it's very difficult to design the devices have 10 different states, but it's quite easy to design the devices to have only 2 states. And sometimes simple means power. For example, how much does a grain of sand weigh? So like 1 grain of sand weighs only about 0.01 grams. But if we're using binary, suppose we double the gram again and again, we can get different weight of the grams. So 1 grain of sand only weighs 0.01 gram. If we have 2 to the 9th power of grains, the weight will be 5.12 grams. It is still very light. Let's continue doubling the number of grains. If we have 2 to the 20th power of grains, we are going to get 10 kilograms of grains. If we have 2 to the 30th power, we are going to get 1073 kilograms. If we have 2 to the 40th power, we are going to get 12,000 tons of grains. Let's take the time as an example. Suppose we double 1 second, we can see the power of binary. So 2 to the 9th power of seconds is actually 8 minutes. And the 10th power of 2 is actually 17 minutes. And the 20th power of 2 is 2 weeks. And 30th power of 2 is already 34 years. And the 60th power of 2 is the age of universe. So binary is also a very powerful number system. Including binary, we also have some different number systems. Like decimal contains 10 digits from 0 to 9, and the base is 10. Binary contains 2 digits, and the base is 2, of course, because it has 2 different digits, 0 and 1. We also have octal. Octal contains 8 digits, so the base is 8. The numbers including from 0 to 7. Hexadecimal consists of 16 digits, so the base is 16. The number including from 0 to 9 and then from A to F. All of the number systems has been widely used in the computer system, but the numbers in different number systems will be converted into binary in order to be processed by the computer. So because we have different number systems, how to distinguish number systems? For example, we have 101. So if we don't know the number systems, we probably think this is 101, which is a decimal. But since we have learned different number systems, this could be different values according to the number system it belongs to. So if it's a binary, we put a subscript 2 here. If it's an octal, we put an 8 here. If it's a decimal, we put a 10 here. If it's a hexadecimal, we put a 16 here. We can also use postfix to represent the numbers in different number systems. So N here means the digits. R here means the number system. So 101B means binary number. 1010 means octal number. 101D means decimal number. 101H means hexadecimal number. Because the number may in different number systems, so sometimes it's not easy to compare the real value of the number. For example, we have this number and this number. It's not easy to know which one is greater or which one is smaller because we have to know the base of the number or the number belongs to which number system. So we have to study the concept of power. So before we're talking about different number systems, let's look at this example. It's quite easy to know 52.6 is greater than 25.6, right? Because they are all in decimal. And we have to calculate the real value of this number by using this way. So 2 here means 20 because the power for this position is 10. And the power for this position is 1. And the power for this position is 10 to the negative 1's power. So we can calculate the real value by doing this calculation. Similarly, we can calculate the real value of this number by using the same approach. And this is the formula for us to calculate the real value of a number. So the real value means the value in decimal because the real value is, designed for human to understand. So here it's a sum of different numbers, and the k here means the number, okay, on different position, and this part means the power of the position. So we can multiply the number and then we add them together. So this is the formula for us to get the real value. And we call this spread numbers approach. So suppose we have 1, 2, 3, 4 in decimal. So the real value will be this one. If we have another number 1, 2, 3, 4 in hexadecimal, we can calculate the real value, use the same approach, but the power will be different because the base of the number system is different. So what we need to do is just change the base. So here shows you the power under different number systems. Of course, in decimal, the power will be, 10 to the highest power. And in binary, it will be 2 to the highest power. And in octal, will be 8 to the highest power. And in hexadecimal, it will be 16 to the highest power. Because here we have the base, which is the number of digits in the number system. So with this approach, we can calculate the real value of different numbers in different number systems so that we can compare the value of the number. And remember that the power for the integer part and for the fractional part is different. For the integer part, the power from right to left will start from 0 until increase 1 by 1. For the fractional part, you can calculate from left to right, and the power starts from -1 and then -2 and then -3, so on and so forth. So this is how we calculate the real value of different numbers. This table shows you a comparison of different number systems. We have the number from 0 to 15 in decimal, And here shows you the corresponding numbers in different number systems. And 0 in binary is 0, and 1 in binary is 1. But 2 in binary is not 2 because we don't have 2 in binary. So we use 1, 0 to represent the 2. Similarly, in octal, we have numbers from 0 to 7, but we don't have 8. So we can use 1, 0 to represent 8 in octal. And in hexadecimal, we use A to represent 10, B for 11, C for 12, and F for 15. So in binary, the 15 will be 1111. In octal, 15 will be 17 because this 1 means 8, this 7 means 7. So 8 plus 7 equals to 15. So these are the numbers in different number systems.